This is a continuation of the gas law tutorial video clip. Just to recap, in the last video clip we looked at the Kelvin temperature scale, and we also looked at how Jacques Charles plotted different types of gases and their relationship between volume and temperature of the gas. And he found that they all seemed to extrapolate down to minus 273 degrees Celsius. It didn't matter what type of gas it was, they all seemed to extrapolate down to minus 273. Now Lord Kelvin took a look at this data and said, well, at this point the volume of the gas should be zero. You can't have a negative volume, so that means you can't get any colder than this. So he decided this number, minus 273 degrees Celsius, would be the starting point for a whole new temperature scale, a scale he would name after himself called the Kelvin scale. While the Celsius scale starts all the way over here and is allowed to have negative numbers, the Kelvin scale is an absolute scale, meaning that there are no negative numbers. It starts off from zero. So, I want you to remember that the Celsius scale and the Kelvin scale are identical. An increase of 1 degree Celsius is an increase of 1 Kelvin. So 0 degrees is 273.15 kelvins. 1 degree is 274.15 kelvins. 2 degrees is 275.15 kelvins, etc., etc. So the two scales are identical. The only difference is their starting point. The starting point for the Celsius scale is here, and the starting point for the Kelvin scale is way down here. So in order to convert from Celsius to kelvins, you just add 273.15. So for instance, 25 degrees Celsius plus 273.15 means that's going to be 298.15 kelvins. If I want to go the other way around from kelvins back to Celsius, you subtract by 273.15 instead of adding. So what I would like you to do right now is to pause the video and try this out for yourself. Tell me, how many kelvins is 13 degrees Celsius equivalent to? And how many kelvins is 125 degrees Celsius equivalent to? And let's go the other way around. If I have 318.30 kelvins, what is that in degrees Celsius? Hopefully this is the answer you got. So in order to go from degrees Celsius to kelvins, I had to add 273.15, and that gave me 286.15. Same thing from degrees Celsius to kelvins. Once again, do the exact same thing. Add 273.15, and you should get 398.15. Now if I'm going the other way, backwards from kelvins to degrees Celsius, you subtract 273.15, and I get 45.15 degrees Celsius. Now, there are several reasons why we have to use the Kelvin scale. You are not allowed to use the degrees Celsius scale anymore from this point on. Let's pretend I have a piece of metal, and the temperature of this metal is 0 degrees Celsius. What if I asked you to heat up the temperature of this metal so that's twice as hot as it was before? Well, what's twice of 0 degrees Celsius? 0 degrees Celsius. Does that make sense? If I ask you to warm up a piece of metal that's at 0 degrees Celsius, so it's twice as hot, and you still end up with 0 degrees Celsius, that makes no sense. Or what would happen if it was negative 5 degrees Celsius, and I asked you, I want you to warm up the piece of ice so it's twice as hot? Well, 2 times negative 5 is negative 10 degrees Celsius, but that's even colder than it originally was. That makes no sense. So as you can see, the Celsius scale does not work very well when we talk about temperature. But since the Kelvin scale never has a negative number, and it's always going to be a positive number, we don't have to worry about that situation. Furthermore, if you look at Charles's law, as well as Gay-Lussac's law, you'll notice that temperature is always in the denominator. So it's V over T, or P over T. Well, what happens if I have 3 liters of gas and it's at 0 degrees Celsius? How can I solve for this? If you punch this in your calculator, it's undefined. So here we have a situation where having negative numbers or 0 numbers does not work very well for our calculations. Which is why we prefer to use the Kelvin scale. Now just so you know, it's impossible, well not impossible, but we don't have the technology right now in order to reach 0 kelvins. It's not possible. We don't have the technology for it. The coldest we can reach is probably minus 272 degrees Celsius, just a few degrees off, or rather a few fractions of a degree off from absolute 0. We are always slightly above the 0. We can never get anything colder than that. We simply don't have the technology. So, because we don't have the technology to reach a 0, you will never reach a situation or encounter a situation where you have 0 kelvins. So that's fantastic for us. So please remember, never, 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 never leave your calculations in degrees Celsius. As soon as you are given a degree Celsius, you must convert straight up into kelvins. Alright, so let's take a look at our 3 gas laws over here. We have Boyle's law stating that P and P1 V1 is equal to P2 V2 so long as the temperature remains constant. Charles' law states that V1 over T1 is equal to V2 over T2 so long as the pressure remains constant. And finally, Guy-Lussac's law, pressure 1 over temperature 1 is equal to pressure 2 over temperature 2 so long as volume is constant. So what we can do instead of having all 3 different types of laws is just combine them all together. And we get the combined gas law. So PV, PV, P2 V2, P2 V2. Notice how in both these cases over here, temperature is at the bottom, so we leave temperature at the bottom. So now all you have to do is just use the combined gas law, and you've pretty much got all 3 of these. So for instance, if I have a situation where I have a constant temperature, well, if temperature doesn't change, it doesn't affect my calculation. So I can just erase temperature, and bam, I've got Boyle's law right there. If I have constant pressure, and if the pressure doesn't change, I can just take it out of my equation because it doesn't really affect it. And there I have it, Charles' law. And finally, with Guy-Lussac's law, at constant volume, if volume doesn't change, well, I can take that out because it doesn't affect my calculation. And there I have it, Guy-Lussac's law. So the combined gas law does the job of all 3 different laws, Boyle's, Charles, and Guy-Lussac's. So let's try this out on a sample problem. When solving gas law problems, I highly, highly recommend that you use the GRASS method. So the GRASS method goes, G stands for given, where you write down all your givens. R stands for required, where you write down what you're trying to find, what you're required to solve for. A stands for approach, where you try to figure out which equation you're going to use. S stands for solve, that's pretty self-explanatory. And the last S stands for sentence, where you write your final sentence. Therefore, the answer is blah, blah, blah. So let's start with our givens. First of all, a sample of nitrogen gas occupies a volume of 300 milliliters. As soon as I see this, I write down volume is equal to 300 milliliters. However, you'll notice that there's another volume over here. So I'm going to write down 1, because this is situation number 1, 300 milliliters. Now, I want you to get in the habit of writing it in liters. So that becomes 0.3 liters, just because later on we'll be using the ideal gas law, and that only allows liters. You can't have it in milliliters, it must be in liters. Next, we see a temperature of 17 degrees Celsius. So we see T1 is equal to 17 degrees Celsius, but like I said before, can't leave it in Celsius, must be converted into kelvins. So can you please convert that into kelvins for me? Pause the video. And hopefully you got 290.15 kelvins, because you had to add 273.15 in order to convert from Celsius to kelvins. And finally, we have a pressure of 100 kilopascals. Now, where most students will make their mistakes is they'll mix things up. They don't know which unit belongs where. So make sure you know that milliliters belongs to volume. Degrees Celsius belongs to temperature, and kilopascals refers to pressure. Do not mix them up. So that's the end of the first situation. Because it's the end of the first situation, I like to draw a little line to remind myself that this is situation number 1. I'm going to start with situation number 2 now. So what volume? So volume 2 is equal to what? That's what I'm trying to find. Will the gas occupy at 100 degrees Celsius? So I write T2 as 100 degrees Celsius, but again, I can't leave it at Celsius, I have to turn it into kelvins. So how many kelvins is that? 373.15 kelvins, because we're adding 273.15 to convert Celsius into kelvins. Alright, and at a pressure of 100 kilopascals. And we write pressure to 100 kilopascals. So R, what am I trying to find? I'm trying to find V2. So, what is my approach? Well, let's write down the combined gas law. And there we have it. Now, this is another reason why I would highly recommend you keep them organized this way, because if you mix up the two temperatures, T1 and T2, you're going to have them on different sides of the equation, and you will not be able to solve it appropriately. So, by organizing your information like this, you are keeping them separate so you know exactly what you're doing over here. Now, take a look at this. Pressure and pressure It's constant pressure. The pressure hasn't changed at all. So if pressure doesn't change, we don't even need to include it in our calculation. So take out the pressures. Done. And so whose law is this? Charles's law at constant pressure. Now S stands for solve. At this point, I'm going to start plugging in numbers. V1 is 0.300 liters. T1 is 290.15 kelvins. Volume 2 is what I'm trying to find. And temperature 2 is 373.15 kelvins. And here we go. Just solved algebraically. And we get a final answer of 0.386 liters. And so that's my final answer. The volume that the gas will occupy at 100 degrees Celsius and 100 kilopascals is 0.386 liters. So the most common mistake students will make in this type of question is A, forgetting to convert degrees Celsius to kelvins. Make sure you do that consistently, otherwise you are more likely to make a mistake. And the second one is just rearranging the temperature volumes by accident. So making sure that you do organize your givens appropriately. Otherwise, if you switch these two numbers, your calculation will be all wrong. So make sure you organize your information carefully. Alright, so let's try one more sample question. First up, set up my givens. So here we go. A balloon at 99.8 kilopascals. Since it's kilopascals, this must be my pressure. And since this is my first situation, I'm going to say pressure number 1. It has a volume of 3.5 liters. Since the units are liters, this must be my volume, and I'm going to say volume 1 since it's situation 1. Now the pressure is then increased. So as soon as I see this sentence over there, I know I'm going to a new situation. So I draw my squiggly line, and I set my new situation. Now it says it's increased by 5.5 kilopascals, so I know I need to add 5.5 to the original 99.8, which means that my final pressure is going to be 105.3 kilopascals. While the temperature rises to 28 degrees Celsius. So I know my temperature 2 is equal to 28 degrees Celsius. So please make sure you know the difference between to and by. Whenever you see the word by, it means you have to add or subtract, depending on whether it's increase or decrease. Whenever you see the word to, that just means that the final value is whatever it states. So it rises to 28 degrees Celsius, 28 degrees Celsius. However, we know that as soon as we see degrees Celsius, you need to convert to kelvins. So I add 273.15 because I'm going from Celsius to Kelvin, and I get 301.15 kelvins. If the final volume, so that means it's going to be V2, is equal to, or final volume of the balloon is 4.2 liters, so I write down 4.2 liters. What was the original temperature? So I need to write down T1 is equal to question mark. So what am I trying to find? I'm trying to find temperature 1. What's my approach? Well, I'm going to use the ideal, or not the ideal gas law, the combined gas law. And as you can see, this is where it comes very, very handy, why we had to originally organize our givens this way, so we can easily just plug and play. Now, here's a little hint. For those of you who have crap for algebra skills, so if your algebra skills are a little wonky, I recommend that you do this. Notice how I'm trying to find T1. Well, T1 is in the denominator right now, and that makes it very difficult if your algebra skills aren't up to par. So what I recommend is, in order to make things easier for yourself, flip it. So we find the inverse. So I put T1 at the top and PV at the bottom. But if I flip it on one side, in order to make it equal, I have to do the same to the other side. Now you'll see that solving for this algebraically should be a little easier than if you had solved it originally like this. Of course, if your algebra skills are fine, then don't worry about it. So let's start plugging in. Pressure 1, 99.8 kilopascals. Volume 1 is 3.5 liters, which equals the temperature 2, 301.15 kelvins. Pressure 2 is 105.3 kilo, and volume 2 is 4.2 liters. So here I've just simplified it and multiplied these two numbers, makes 349.3. Keep that one over there, and multiply these two numbers and you get 442.26. Now we just get rid of this 349 by multiplying out. and we get 237.85. Please remember that this is in kelvins, so in reality it's actually only negative 35.3 degrees Celsius. But since we usually answer our questions in the form of kelvins, this would be my final. Alright, since my time is running up again, I will finish up our last two laws, the ideal gas law and also Avogadro's law, in the next segment.